Now let's talk in detail about ionic bonding and covalent bonding, and if time is left, then if we have time, then we'll talk about metallic bonding as well. Now first let's talk about ionic bonding. Now first of all, let's define ionic bonding. So this is the electrostatic force of attraction that exists between oppositely charged ions due to the transfer of electrons from the positive metal ion. The transfer of electron is always from the metal to the non-metal, so this transfer is from the positive metal ion to the negative anion. Alright, and hence because you've got oppositely charged species, so they're going to attract as a general rule of thumb, and if they attract one another, they're going to stay with one another, and hence they will form a giant lattice structure. So whenever describing the structure of an ionic compound, you always mention the term giant ionic lattice or giant lattice structure. Alright. Now, the melting and boiling point and the physical properties of ionic compounds depend upon the ionic bonding in them. The stronger the ionic bonds, the greater would be the melting and boiling point. Ionic bonds in general are stronger than intermolecular forces, namely hydrogen bonding, PD-PD, and ID-ID. Alright, so if you compare the melting and boiling point of sodium chloride, which is an ionic compound, the normal table salt that we've got, against HCl, which is a volatile liquid, or a volatile liquid or gas, then that obviously makes sense, because sodium chloride has strong ionic bonds which require much higher energy compared to the van der Waals forces in HCl, compared to permanent dipole interactions in HCl, and hence HCl is a liquid or a gas. Alright, so this is a question that is usually tested. You have to compare a compound, a solid, which is generally an ionic solid, against a simple molecular structure. That's the first question. Another question that might pop up, and that usually has actually come on your exam, is comparing sodium chloride against magnesium oxide. Alright, sodium chloride against magnesium oxide. How would you compare their melting and boiling points? Okay, so first of all, well, think about this. Which one might have a higher melting and boiling point? Now see, magnesium is a divalent ion. Alright, it has a charge of +2, whereas sodium has a charge of +1 only. So this means that magnesium would have double the charge of sodium. So the ionic bonds that magnesium will form with oxygen are going to be 2 times as strong as that of sodium, right? So they're going to be 50%. There would be a 50%, it's doubling, 100% increase in the strength of ionic bonding, right? This is actually an exam question, AS question that came up on the exam, in which it was asked, why is this jump so big in the melting point? So it was because the charge on the positive ion is doubling as we go from sodium to magnesium. So therefore, magnesium would have much stronger ionic bonds compared to sodium due to the double charge. All right. And hence magnesium oxide would have higher melting and boiling point compared to sodium chloride. All right, this question is very frequently tested, so make sure you know the answer to this, because of this the reasoning that I told you right now. Now, apart from ionic compounds compared against itself, and ionic compound compared against the non-ionic compounds, let's come to covalent compounds. Now, covalent compounds are of 2 broad categories. We've got simple covalent and we've got giant covalent. Simple covalent are also known as simple molecular structures, whereas giant covalent are the 3 broad categories that we have got. But right now, the simple molecular ones that we've got are halogens in general, all right, starting from fluorine, chlorine, bromine, iodine. They're all simple molecular. Simple molecular, usually their melting and boiling point and their physical properties, it depends on the intermolecular forces, the type of intermolecular forces that they might have, all right. They can have hydrogen bonding, they can have permanent dipole, they can have ID forces depending on what type of molecule it is, whether it's polar or non-polar, whether it has nitrogen, oxygen, or fluorine or not. And then apart from that, what we do have are the giant covalent structures. Now, giant covalent structures are those which have a lattice structure, which have a big arrangement, a giant arrangement of atoms linked together by strong covalent bonds. And their melting points actually depend on the covalent bonds themselves, not on intermolecular forces. All right, so make sure, this is an important term to note over here, that Simple molecular structures, melting and boiling point and physical properties, all of them depend on the intermolecular forces that we have done so far, whereas the giant covalent structures, melting and boiling point and physical properties depend on the covalent bonds themselves, right? Silicon dioxide, carbon, graphite. Carbon has two allotropes. Allotropes means alternative forms of the same element. Now, carbon and graphite have giant covalent structures. Reason? Because in carbon, in diamond, each carbon is bonded to 4 other carbon atoms, which in turn are bonded to 4 more carbon atoms, forming a giant lattice arrangement, tetrahedral structure, 109.5 bond angle, sp3 hybridization. All right. In graphite, however, each carbon is bonded to 3 other carbon atoms. So per carbon atom, you've got 1 extra free electron, which can move over the layers of graphite to conduct electricity. And by the way, because each carbon is bonded to 3 other carbon atoms, therefore you've got a whole layer of hexagonal rings. All right. And on top of those layers, you've got the electricity passing because of the extra free delocalized electron on the structure of graphite. And graphite is the only giant covalent structure that can conduct electricity, and this is a question that was asked. And the reason for that is because each carbon atom is bonded to 3 other carbon atoms due to sp2 hybridization and having a bond angle of 120 degrees. So 1 electron per atom in graphite is free, which can conduct electricity. All right. Now, this is a question that why does graphite conduct electricity and why doesn't why doesn't diamond conduct electricity? So the answers are already given to you. Because diamond has a giant covalent structure, tetrahedral structure, all electrons are involved in bonding, nothing is free, so no electricity conduction. In graphite, there is 1 electron per carbon atom, sp2 hybridization, 120 degrees bond angles. Electrons are free to move around here and there, so they can conduct electricity. And apart from graphite, we've got silicon dioxide. So in silicon dioxide, each silicon is bonded to 4 oxygen atoms, but each oxygen is bonded to 2 silicon atoms. And around the silicon, you've got a tetrahedral structure. Around the oxygen, you've got a bent structure. All right. So around the silicon, you've got 109.5 degrees bond angle. And silicon dioxide also does not conduct electricity. Silicon dioxide is actually the soil that you see around yourself. It also has a giant covalent structure, therefore the highest boiling point and melting points due to a giant covalent structure of multiple covalent bonds. Okay. Diamond by far in all of our compounds has the most melting and boiling point due to its highest due to all the carbon atoms being involved in bonding and due to its giant covalent structure. Okay. Now the question that usually comes, first of all, describe the structures of each of these giant covalent structures. They can ask you to describe the structure of diamond, describe the structure of graphite, describe the structure of silicon dioxide, and I just did that. I literally did that right now. Next, they can ask you to compare why the electricity question, why does graphite conduct electricity and why does any other element conduct electricity. Next question that can be asked is hybridization. What is the hybridization of graphite, diamond, silicon dioxide, silicon? But usually they ask about carbons, okay, in diamond and graphite. All right, the definition of allotrope. So allotrope means alternative form of the same element, right? Element. So both diamond and graphite are alternative forms of the same carbon element. Then apart from that, they ask you to compare and contrast the physical properties of the giant covalent structures against the physical properties of ionic bonds, ionic compounds, for example, or simple covalent compounds. Regardless of whatever they compare, always mention that whenever you have a covalent structure, a giant covalent structure, it's always the giant covalent structure that will have the highest melting and boiling point and the most rigorous properties because of the giant covalent structure, because of the strongest network of covalent bonding. All right. So the answer, if I was asked to compare, the question was, okay, why does diamond have a higher melting and boiling point compared to sodium chloride? So the answer for that, the first point would be diamond has a giant covalent structure, whereas sodium chloride has a giant ionic lattice. That's the first answer that I have to mention. I need to identify the types of bonds that they have. Then the next is ionic bonds are much weaker compared to the covalent bonds that we've got in diamond and graphite and silicon dioxide occur in diamond. Therefore, more energy is required to break the giant covalent structure of diamond as compared to sodium chloride. Okay, so we've actually answered this question. About electricity, done. Structure, done. All right, what else do we have in here? Okay, I guess that's about the giant covalent structures. Okay, now after giant covalent, yeah, and graphite is used as a lubricant. Why is the graphite used as a lubricant? Even though there's such a high melting and boiling point, it's still soft. Why? Excuse me. Okay, so why is graphite soft? So the answer to that is because in between the layers of graphite, you have empty spaces. You have weak you have weak van der Waals forces or IDID forces in between the layers. The graphite hexagonal ring layers. In between the layers, you've got weak intermolecular forces. So when a force is applied across the layer of graphite, the layers can slide over one another, providing it soft, lubricating properties. Therefore, graphite is used as a lubricant. Next question can be, why does graphite conduct electricity, whereas solid sodium chloride does not conduct electricity? Or compare and contrast the electrical conductivity of graphite against solid sodium chloride. That is a valid question. So the answer to that is, now whenever you are mentioning the electrical conductivity of ionic compounds, always remember the fact that ionic compounds only conduct electricity when they are either dissolved in an aqueous solution or are in the molten state, meaning in the liquid state. And their ions are charged particles. Ions can conduct electricity, but only when they are allowed to do so, meaning only when they are free. So if the ionic compound is in the solid, in the liquid state, meaning the molten state, or in the aqueous state, then can it conduct electricity? Okay. So if you're asked about solid sodium chloride, the ions in solid sodium chloride are fixed, therefore they won't conduct electricity, whereas in graphite you've got one free electron per carbon atom due to sp2 hybridization. Therefore, graphite will conduct electricity and solid sodium chloride will not conduct electricity. Okay, so you have to compare and contrast the electrical conductivity of the two species. Now once we are done with that and we are done with the normal covalent bonding, okay, how is covalent bonding formed? So you know that it is formed by the sharing of electrons. If one electron is shared by each of the atoms, that forms a single bond. If two electrons are shared by each of the atoms, that forms a double bond. And if three electrons are shared by each of the atoms, that forms a triple bond, right? But what about the other category, the special type of covalent bonding, which is known as a dative bond or a coordinate covalent bond? Now, coordinate covalent bond by definition is a type of bonding in which both the electrons are provided by one of the two bonded atoms, all right? That in this case we've got a donor atom and an acceptor atom. All right, example I gave in the previous videos was ammonium ion, which is formed when ammonia molecule accepts a proton, accepts a hydrogen. Now hydrogen positive ion does not have any electrons. Hydrogen positive ions has a free vacant orbital, right? That is completely empty. It doesn't have any electrons inside of it, whereas ammonia has, the nitrogen of ammonia has a lone pair of electron on top of the ammonia nitrogen molecule. Now that nitrogen is the donor, it can act as a donor atom, whereas hydrogen can act as the recipient or acceptor atom. Now hydrogen has a vacant orbital, whereas ammonia's nitrogen is the donor atom. So ammonia's nitrogen is going to use its lone pair of electrons to form a dative bond to provide both the electrons and form a dative bond. You're going to form a curly arrow, and the dative bond from the lone pair of electrons will be used to form a bond, to form a covalent bond with the hydrogen. Now hydrogen will be accepted and the positive charge of hydrogen will be removed. The reason for that is because now once a dative bond is made, it acts as a normal covalent bond, meaning both the electrons that the nitrogen was providing, they would be equally distributed between hydrogen and nitrogen, and then one electron will belong to nitrogen and the other electron will belong to hydrogen. Now after the dative bond is made, it acts as a normal covalent bond. It is no longer a dative bond. All right, so therefore the positive charge which was first on hydrogen now has been shifted to the nitrogen atom. Reason? Because nitrogen has technically lost one electron. Hydrogen didn't have an electron initially, right? Nitrogen gave that electron to hydrogen, but it didn't completely transfer it. It was in between the two atoms. It was in between the nitrogen and hydrogen, if you can understand what I'm saying. Therefore, this fourth bond within the ammonium molecule is the dative bond, which results in a positive charge on top of the nitrogen atom. Alright, so you have an NH4 positive ion. Now, once the NH4 positive is made, the nitrogen no longer has a lone pair, it has 4 bonded pair of electrons. Hence, the shape of the shape around the nitrogen atom changes from trigonal pyramidal, which was in ammonia, 107.5 degrees, to tetrahedral, which is an ammonium ion, which is 109.5 degrees. Alright, so that's dative bonding. And ammonia converting into ammonium is a very common example. Apart from that, we've got some other examples as well, but they are covered in organic chemistry, so I'll try my best to cover that in these rapid revision videos as soon as possible. But yeah, that's that. Now next, after we are done with ionic bonding and covalent bonding was actually a lot, okay? After covalent bonding, we've got metallic bonding. Now, metallic bonding is also an electrostatic force of attraction, but it's an electrostatic force of attraction between positive metal ions and a sea of delocalized electrons. Now, make sure to use these terms as I've used them, because these are the key terms: sea of delocalized electrons, sea of mobile electrons, and positive metal ions. Some students just mention that it's an interaction between metal atoms and electrons. That's totally wrong, because it's losing a lot of key terms, okay? The student other day from the international school actually came and he had his definition marked incorrect, and that was actually incorrect because it was incorrect. It was missing a lot of key terms, okay? So make sure to include these key terms, that it's the electrostatic force of attraction, first of all, between the positive metal ions and a sea of delocalized electrons surrounding it. And remember, for metals, the melting and boiling point depends on the metallic bonding. It does not depend on the ionic bonding, it does not depend on the intermolecular forces, it does not depend on the covalent forces. It only depends on metallic bonding. All right, so certain metals, now the sea of delocalized electrons that you have over here are actually electrons from the valence shell of the atoms. All right, so if you go from sodium to magnesium to aluminum, the electrons in the sea of delocalized electrons increases because their outer shell electrons also start increasing. In sodium, there's just 1 electron per atom in the outer shell. After that comes magnesium, which has 2 electrons per atom, and then comes aluminum, which has 3 electrons per atom in the outer shell. Therefore, aluminum has the highest electrical conductivity compared to sodium and magnesium. That's also a question. If you have all 3 of these elements, which one will have the highest electrical conductivity? And the answer to that is aluminum. Then if you compare sodium to magnesium, you can easily say that it's magnesium. And if you have sodium against aluminum, then it's easily aluminum. Aluminum has the highest electrical conductivity. Usually it is aluminum that they ask. So the reason for that is because it has the greatest number of valence shell electrons, which it can provide to the sea of delocalized electrons, hence have the strongest metallic bonds. All right, and if you are asked to compare and contrast the melting and boiling points of aluminum against sodium chloride, then you know what to do. The first step is always to identify the type of forces that are present inside of them that is responsible for the melting and boiling point. For example, sodium chloride has ionic bonds, whereas sodium alone has metallic bonds. So obviously, and if they have given you some values, so then you would say that yeah, the ionic bonds are stronger or the metallic bonds are stronger, depending on whatever values they have given you, and then you can answer it. All right, then if they ask you about let's say the melting point of aluminum, why aluminum is a solid whereas chlorine is a gas. If this is the question, then you know what to do. Always the first step, always stick to the basics. First, you identify the type of forces that are responsible for their melting and boiling points. So in sodium or in magnesium or in the metal, you've got metallic bonds, whereas in chlorine, you've got ID forces. ID forces are way weaker compared to the metallic bonds. Therefore, the metal is a solid. It has a giant metallic lattice. You also have to mention that as well. It also has a mark, okay? Whereas chlorine is a simple molecular structure. So 2 marks. And so number 3, the metal requires much more energy compared to chlorine, and hence is a solid state. Okay? So this technically should finish off your metallic bonding, covalent bonding, ionic bonding, and in the previous videos we've covered hydrogen bonding, permanent dipole, and ID forces. And we've also covered in covalent bonding, we've covered the normal covalent and coordinate covalent, which is coordinate covalent is also known as dative bonding. So that's pretty much it about it. Now I would recommend quickly going over the past paper questions. All right, I've actually summarized most of the past papers of paper 2 and paper 4 in these videos, but make sure to go through the past paper videos, past paper lectures immediately after watching these videos. All right, and if you want personalized lessons of A-level chemistry, you can contact me over my WhatsApp number, which is probably going to be in the description. If not, then you can contact me on my WhatsApp, on my main YouTube channel, or wherever, and then my team would probably get back to you. All right, so that's it. Thank you so much.